For most of my life, I've given little thought to soil. To me, it was a flat surface that I walked on. I've been thinking a lot more about it these days, and what I learned has surprised me. I learned that soil is like the Earth's skin that lies between the sky and its rock core. It's where plants keep a tenuous grip with their roots as they harvest the sun's energy with their leaves. I began to realize that soil is alive, and that a handful of good soil contains more living things than all the human beings that were ever born. It dawned on me that without soil, life as we know it would not exist. If soil is alive, I wondered if a soil could die. I visited with Pam Thomas and spoke to her about this.
A recent historical example is the Dust Bowl. In the early part of the 1900s, homesteaders plowed up millions of acres of prairie lands in order to plant crops, mostly wheat, because wheat was bringing very high prices during the World War I wheat boom. Well, because of this intensive cultivation, the delicate balance, the ecosystem was essentially destroyed. You had the plants, the animals, and the microorganisms, to the point to where the soils were no longer able to function. So as the wet years of the 20s gave way to the drought of the 30s, the soil, which no longer had the natural anchors to keep the soil in place, became very susceptible to wind erosion.
In fact, in the 1930s, dust storms would start in the Great Plains and would move cross-country to places like Boston and D.C. Meanwhile, in the southern U.S. Piedmont, plowing and monoculture crops destroyed soil, causing massive gully erosion. Some of these gullies are still visible today. No wonder FDR said that the nation that destroys its soil destroys itself. These were dramatic examples of soil destruction, and I got to thinking how we were doing today.
We are still losing soil today. It's not as obvious to us today as it was during the Dust Bowl 30s, but it's an ongoing crisis because the bottom line is that we are feeding more and more people on fewer and fewer acres. We are literally losing ground.
The naturalist Aldo Leopold warned us that one of the dangers of living away from the land is that we are inclined to think that our breakfast comes from the grocery store, or a carton. This got me to wondering how much soil we had to feed our planet. My soil scientist friend Jackie helped me understand this. Imagine for a moment that the Earth is this apple. 75% of the Earth is covered by water. Now half of the dry land on our planet is too hot, too cold, or too dry to produce food for humans. Of this amount, about half is too rocky, steep, or too shallow to produce food. It doesn't take a rocket scientist to figure that there's not much left over. And then what we have left is under pressure from things like urban sprawl and erosion. It takes 500 years to form an inch of soil, something that can be destroyed in a few minutes, and that worries me. Leonardo da Vinci said that we know more about the movement of celestial bodies than about the soil underfoot. I'm guilty as charged, but I'm not going to leave it that way. Join me in the rest of this series to find out what soil really is and what it means to us. Perhaps if we learned more about soil, we'd be better equipped to take care of the planet. If life as we know it depends on the soil, it stands to reason that what happens below the soil surface has a profound influence on what happens above the surface. My knowledge of soils needed to run deeper. The people that could help me do this were the soil scientists. Their work is to look beneath the surface into this life-giving yet unseen world. Each day in the field is an adventure of discovery for them. They have their own vocabulary, and they love the feel of dirt in their hands. This was the Soil's dream team, and they would be my teachers for the next few weeks. Dennis is a veteran who has mapped over 1 million acres of soils in his lifetime. Lance and Emery are also seasoned soil explorers who have discovered a new soil series that bears their respective names. This was going to be fun. The first thing they showed me was how the soil was formed. This happens when weather and living plants and animals break down loose rock called parent material. Parent material is typically weathered bedrock that over time becomes the main mineral component of the soil.
It looks like rock when you dig it out, but as you can see, it's very friable, massive structure, breaks easily.
Dennis took me to a road cut to show me that over time, soil is formed in layers called horizons. These horizons tell us about their history, and they can also give us clues about their future.
This is the A horizon, or the surface layer. Look at all those roots in there. That's wonderful. The dark color is caused by the organic matter in there. And here we have what's called an E horizon, capital E. Fairly light in color, more sandy in texture. And down below it is our B horizon that contains much more clay. And you can see is much more red down here too.
Each soil horizon has unique properties like depth, color, or clay content. When these horizons are layered on top of each other over time, they form soil profiles which can be identified by name. They are often named for the place they were first identified, like Norfolk or Durham. When it comes to looking below the soil surface, nothing is as effective as a good old-fashioned soil auger. You'll never find these guys in the field without one. I guarantee it. Now I began to see how soil profiles can tell their story, layer by layer.
This is a soil profile put into a long tray so we can look at it a little easier than it's pulling it out with the auger. In this hand here, you'll see this is the A horizon. You'll see it's much darker because it contains organic matter in here. This is the A horizon, or the surface layer. This is 8 or 10 inches below the surface. And see how red this is? All soils contain iron. And we know if we put a piece of iron outside for 2 weeks, it turns rusty. This is rusty soil.
Rusty soil, how about that? So each color has a different meaning. Bright reds and yellows mean that a soil is well drained. There's more oxygen in the soil to oxidize or rust the iron in the soils. Gray colors, on the other hand, mean the soil is waterlogged for most of the year because there is less oxygen to get at the iron. A dark brown color means more organic matter, which is mostly in the A horizon or topsoil. We can use the Munsell color book to classify the exact color of the soil.
We take the soil ped and put it behind the book and find the color shift that it most resembles. I'm going to say it's that color there. 2.5 YR 48.
2.5 YR 48, by the way, is a more precise way of saying red. Dennis also pointed out to me that soil depth is another way to identify soils.
This is the Cecil series because the clay content extends below a 30-inch depth. If this clay content decreased above a 30-inch depth, they're called the Packlet series. They're kissing cousins.
Whoa, kissing cousins? It turns out that if two soils have similar color and clay content, but different depths, they'd be named differently. At this point, I knew enough to see how you could identify specific soil series. I was now ready for Lance and Emery to show me their newly discovered soil. It's named the Bruback series.
Right there, about 22 inches, we're starting just to barely nip on the CR material. You can hear the grind and feel it in the auger.
Right here we have the A horizon. It's about 6 inches thick, and it's a fine sandy loam. Then we get into the B horizon, which is a heavy clay. And here about 12 or 15 inches we have the gray colors coming in. And for a brewback soil, we have to have the gray colors within the top 10 inches of the B horizon. As we move on down in the profile, about 20 inches, we get this sandy clay loam, which is the BC horizon, which is a transition between the B horizon and the parent material.
By this time, I had seen a few soil series, each with its own color, depth, and clay content, each with its own personality, if you will. It turns out that soil scientists have identified and mapped over 19,000 different soil series in the country. That sounds like a huge effort. I had to find out who was doing the work and why it is so important. I found out that the massive effort of identifying and mapping soils is known as the Soil Survey. The body of information resulting from this ongoing effort, also known as the Soil Survey, is available in hard copy and online at the Web Soil Survey. It's an inventory of soil maps, soil properties, suitabilities, and limitations. I was reminded that what happens beneath the surface of the soil ultimately affects everything above its surface. Everything. That's what makes the Soil Survey so important to any land management decision, from farming to disaster recovery planning. I drove out to Lee County to find out who the people were behind all this work and how soils were mapped. Charlie is a soil scientist who is responsible for the upkeep of about 11 million acres of soil survey.
Most of this, well, all of South Carolina has been mapped. So what we're doing is updating all the older soil surveys.
He offered to take us through the process of making a soils map in the field, and I asked him to sketch out the day for us.
One of the things we do when we go through the process of making the soil map is to stand and just look at the area and take in the whole landscape itself. And you can see out in this part of the world that some areas of it are concave, some of it are more convex. So essentially what we do is to stand out here and note where these areas are, dig the holes, identify the soils, and label them on the map using alphanumeric symbols. The finished product looks like this. This is the same area that we're standing in, and we can see that these soil lines delineate the different tones on the map.
The first hole we dug was on a slight rise. We then moved over to a slightly lower area only 300 feet away and dug another hole. Charlie showed me the difference between the two soils that were so close to one another and how landform influenced them.
This soil in the front is the Rain series. The soil in the back is the Norfolk series that we looked at earlier. One of the first things we notice is that the surface of the Rains is darker, and that is reflected by the tones on the map. The other obvious thing is that the subsoil is much grayer. Where the Norfolk series is dominantly brown, the Rains is dominantly gray. The grayer colors immediately below the surface means that this soil formed and still at times will have a water table at or near the soil surface. And although these soils are only 300 feet apart, the water table is the limiting factor on land management here in the coastal plain. Part of the process of making a map is to ask the questions and then to go get the answers. And once we've identified some soils in the area, we begin to understand that the same soils more than likely will be occurring in that area.
It looked like Charlie asked and answered a lot of questions. I don't know how many miles he walked, but he mapped 300 acres that day. Many of my conservationist friends tell me that a bad day in the field is better than a good day in the office. I began to reflect on my newfound appreciation for the work that Charlie and his colleagues do in the soil survey. My knowledge of the big picture was taking shape, but I wanted to see the area we had mapped in the Web Soil Survey for myself. Back at the office, I went to the Web Soil Survey and found the place we had mapped in Lee County. I drew my area of interest boundary and went to the Soils Map tab. All the familiar soils, Goldsboro, Naboko, Norfolk, and Rains appeared. I was in the right place. Charlie had told me that depth to the water table was the limiting factor here, so I went to the Soils Data Explorer to look at the soil's properties. Sure enough, the Goldsboro and Rains soils had shallow water tables as we had seen in the field. I then had a look at the soil's suitabilities and limitations for land use to see where the best place to, say, build a house would be. It turns out that if I were to do that, it was better on a Norfolk soil and maybe on a Goldsboro. All of the other soils were going to be too wet. I used the shopping cart feature, which was free by the way, to get a custom soil survey report, a little memento of my day in Lee County. What I had learned so far showed me the broad brushstrokes of soils in the landscape and how they affect so many of our above-ground land management decisions. I now wanted to see the soil from a different perspective. To get really up close and personal with soils, I visited with my good friend Richard in his garden.
We moved into our house about 1984, and we always had the hopes of having a garden. We've tried a whole different groups of things. We've always had tomatoes and squash, different kinds of squash, zucchini, yellow squash, and melons, cucumbers. That's been the basis. Now we've gone from about 1/2 inch of topsoil to about 8.5, 9 inches. So it'll be good for the next people who move in. They'll be able to use the soil well. And now we're trying to do a no-till garden, so that's a new step in our direction.
To take a close look at Richard's soil, we took a sample and put it under a microscope. The first thing we noticed was that the soil was made up of both mineral and organic particles. The next thing we noticed was how much mineral particle size varied. It turns out that mineral particles can be classified by size, sands being the largest and clays the smallest. Sand is gritty to the touch, while clay has a sticky feel to it. Pure silt, not very common in the southeast, feels like talcum powder between the fingers. The mix of these sand, silt, and clay particles in a soil is known as soil texture. Clayey soils are fertile, but they don't always drain well. Sandy soils, on the other hand, drain very well, but are generally not fertile. The soil in Richard's garden contains about 40% sand, 40% silt, and only 20% clay. This would make it a loam, the soil texture that combines both good drainage and fertility. If you hold Richard's soil in your hand, you can see that it clumps together nicely into soil aggregates. Soil scientists call this aggregation property soil structure. Keep in mind that structure is a different soil property to texture. Soil aggregates, or soil PEDs, can be classified by size, shape, and strength. Good soil structure is important in soils because water, air, nutrients, and roots will find it easier to move between soil aggregates than through them. One of the surprising discoveries I recently made was that in an undisturbed soil, about half of the soil's volume is made up of spaces. These spaces are vital to the health of the soil because they contain air or water. It's in these spaces where soil chemistry and biology are at work. Soil scientists tell me that these are called pores. pore spaces. If they are between sand, silt, and clay particles, we call them micropores. The much larger spaces we found between soil aggregates are called macropores. Macropores are especially important because they become the superhighways for air, water, and nutrients to reach plant roots. Richard put his rototiller away a few years ago. Less disturbance by rototilling has benefited his soil by preserving those pore spaces. More spaces for air, water, and roots in the soil means more vegetables on the table for Richard and his family. I had always thought of pH as a property of water and not soil. Lemon juice has a pH of about 3, that's acidic, and baking soda has a pH of about 9, that's basic. Pure water, which is neutral, has a pH of 7. Now that I realize that more than a quarter of the volume of soil is water, this makes sense. The water chemistry in those pore spaces is critical to how plants absorb nutrients from the soil. Richard usually gets his soil tested at the local extension, but pH test kits like this are available online or at local stores.
So between 6 and 7?
His soil is slightly acidic, but it's in the range where most of his plants thrive. If the pH is too low, his plants will not be able to take up nutrients like nitrogen and potassium. If the pH gets too high, his plants would have problems absorbing iron, manganese, and zinc. So keeping that pH in the 6 to 7 range is really critical. As we finished up our visit, Richard shared some of his land philosophy with me.
I believe in stewardship. If you're given something, can you make it, improve it, and can it be better for the next person? So we've done everything we can to help it to be someplace that people will enjoy later.
That got me to thinking. Richard's soil is a sisal. That won't change. But it was clear that there were some properties in the top 6 to 9 inches of sisal soil that he had improved through good management. It means that a sisal soil could be healthy or unhealthy depending on how it's managed. A healthy or unhealthy soil? This was a fascinating concept that I had to explore further. I spoke to Pam and told her about my experience and asked her if management made a difference to the soils. She replied with a story from the famous soil scientist and father of soil conservation, Hugh Hammond Bennett.
In the early part of his career in the 1900s, he and a colleague were wandering around when they noticed 2 pieces of land side by side. These 2 pieces of land looked vastly different in terms of soil quality. It was obvious that these 2 areas at one time had been identical. They had the same geology, the same slope, and the same climate. However, in one area, the soil was soft. It was loamy and moist enough that they could dig it with their hands even in dry weather. The other area, in contrast, was very hard and dry. It was almost like a brick. They could not dig it at all. The difference between these 2 is that the soft one, the mellow one, was under a dense forest, while the other one had been continuously cultivated for decades. Mr. Bennett, or Big Hugh, called this his epiphany.
Big Hugh's epiphany was about how management can change soil function. Put in the simplest terms, soil function is its ability to moderate water flow and storage, to store and recycle nutrients, and to sustain life. In the spirit of Big Hugh's epiphany, I did a simple test to see how well soil structure holds together in water. It's called the Slake test. I took 2 soils, both from the same soil series. One was continuously cultivated, and the other had been under no-till and cover crops for years. The no-till soil measured out at 3% of carbon-rich soil organic matter, the paler tilled soil at less than 0.5%. It didn't take me long to figure which soil was healthy. It's no wonder so many of our Piedmont reservoirs are the color they are. The difference in the way the two soils behaved is about glue and string. Soil life, roots, earthworms, fungi, and bacteria secrete biotic glues. Roots and fungi also form biotic string, which works with the glues to form a sticky network that holds soil particles together. The glue and string is what keeps the pore spaces between the particles open to provide a place for water storage and flow, and to provide a habitat for all of the soil organisms. This allows water to be stored and to move through the soil when it's needed. The easiest way of damaging the glue and string is by disturbing the soil. Soil disturbance chops up the biotic string and allows piranha-like bacteria to gobble up the carbon-rich string and the glues, turning them into carbon dioxide and releasing them into the atmosphere. When I removed the soil organic matter, the pore spaces collapsed and I was left with empty dirt. Any kind of soil disturbance will do this. The more intense, the more of the soil will be damaged. If Big Hugh were still around, he'd have a fascinating conversation with today's soil ecologist. They'd tell him that the glue and string are part of soil organic matter, which consists of decomposable organic material, humus, and living things. The decomposable organic material is like the pantry for many soil organisms. Humus, dark and sponge-like, is a very stable organic substance that remains after many soil organisms have used and transformed the original decomposable material. One of the functions of humus is to be a sponge that holds water for drier weather. About 5% of the soil organic matter's mass is made up of living things, microscopic soil bugs or soil microbes, and animals that we can see without a microscope. The weight of the microbes alone under 1 acre of this soil surface is more than this cow-calf pair. That's a lot of microbes. It's the soil biology that regulates about 90% of the soil's function of moderating the flow and storage of water, nutrients, and energy in your backyard, in the farm field, on our planet. I still worry about urban sprawl and erosion, and the amount of fuel and fertilizers we use to make food. But there's good news. Soils are resilient and forgiving. From the Carolinas to the Dakotas, farmers and gardeners are restoring soil health by working with nature, not against it. They've stopped tilling completely. They've started growing multi-species cover crops that feed and cover the soil. It's growing them more and costing them far less. In the cities, they're planting trees and rain gardens, restoring old buildings instead of breaking new ground. School kids are learning more about soils. That's huge. In these last few months, I've come such a long way, and yet where I stand now, I see how much more I have to learn. Sometimes I feel all of this can be overwhelming, but when I think of Big Hugh and what he went through, I think he'd tell me that there's hope. I bet he'd like us to call it humic hope.